Good afternoon, advanced algebra students. I hope you're having a great day. It's actually a Friday afternoon, and I am recording these notes for you just so that they'll be ready when you need them. We are on section 6.3. So far in this chapter, we've learned some meaningful applications for exponential functions in areas such as population growth or investments. In these previous examples, the value of the exponent was time, and that was always something we knew. However, when the exponent is something we don't know, when it is our unknown, we can use something called logarithms to solve for the exponent. Now, I know this is going to sound a little bit strange, but I think logarithms are a lot of fun. So I'm looking forward to showing you guys how these work. So logarithmic functions are the inverses of exponential functions. So the logarithmic function, y equals log base b of x, is the inverse of y equals b to the x. So exponential functions and logarithmic functions are related to each other because they are inverses of each other. Now, there are two ways we can kind of go back and forth between logs and exponents. The log base b of x equals y is equivalent to b to the y equals x. So I want you to notice that in both of these cases, the b is our base. And that can be helpful in understanding and working back and forth. So let me show you how it is that we can convert back and forth between exponential and logarithmic functions. So let's say, for example 1, I know that 3 to the power of 4 equals 81. If I want to write this in an equivalent manner using logarithms, I can use a heart shape here. I can say log base 3 of 81 equals 4. So log base 3 of 81 equals 4. All right, let's look at example number 2. In this case, I know that 7 to the power of 3 is 343. Again, I'm going to start on my base and draw a heart shape going to the right and rewrite this as log base 7 of 343 equals 3. All right, now let's take something in logarithmic form and put it in exponential form. So example 3. If I have log base 5 of 25 equals 2, and I want to rewrite this in exponential form, I can say 5 to the power of 2 equals 25. Notice that both of these are true statements and they are equivalent to each other. They're just in different formats. All right, let's try another one. Let's do example number 4. If I have log base 2 of 32 equals 5, and I want to write that in an equivalent manner using exponents, I can say 2 to the power of 5 equals 32. Now, another way that we can deal with this kind of problem is to evaluate logarithms. So for example, let's say that we were asked, what is the value of this logarithmic expression? Log base 5 of 125. What I like to do, because I'm more of a visual learner, is I like to put an equals x here and then rewrite this in exponential form. So 5 to what power equals 125? I can check subsequent values of x and see what works. 5 to the power of 1 is 5, 5 to the power of 2 is 25, and 5 to the power of 3 is 125, so I know that x is 3. Let's go ahead and try some that are just a little bit more challenging than that one. So we'll start out with, the next one will be example number 6. So example number 6, let's take log base 1/4 of 16. If I would like to evaluate that, again, I'm going to put a little equals x here, and I'm going to say 1/4 to the x power equals 16. Now this can look a little bit confusing at first, but what we want to do is ask ourselves, what is a way that we can relate 4 and 16 using exponents? I know that 4 to the power of 2 is 16, and so what ends up working here is -2, and let's see why. If I take 1/4 to the -2, that becomes 4 squared over 1, or 16, because the negative sign, remember, is what causes me to put the 4 down below. So in this case, I can see that x is 4. Let's do another very common type of problem that comes up. Log base 3 of 0 equals x. Actually, I was thinking of another one. This one is not super common, but let's see what it says here. 3 to what power is 0? This would be undefined because there is no power that we can raise 3 to and get 0. All right, I want to show you a shortcut here that sometimes comes into play. So this will be example 8. Log base 2 of 2 to the 8 equals x. We can do this by making a heart shape here and saying 2 to what power equals 2 to the 8, and then we can say, oh, x would have to be 8. But something that you should know is if you take a log with a base and then this number here is that same number, you can kind of think of them as canceling each other out, and so you would just get x is 8. Let's talk about some common logarithms and natural logarithms. So a common logarithm would be log base 10 of x. We can just call this log of x for shorthand, so they are equivalent. Another very common logarithm is the natural logarithm. So log base e of x, we just call ln x. There are buttons for the log of x and ln x on your calculator. So let's use our calculators to evaluate some of these. Example number 9. If I wanted to take the log of 900, that would really be saying log base 10 of 900 equals x, or 10 to what power equals 900. But on my calculator, I can simply plug log and 900 in, and then I'm going to get that x is 2.9542. All right, to solve equations with logarithms, there are a variety of processes that we can use. So let's do a few examples to give you a little bit of practice. Let's take a look at the equation 25 equals 10 to the x minus 1. Now I have to say, for me, I find this easier to do if I always put the base on the left. So I'm going to draw my heart shape, and I'm going to write this as log base 10 of 25 equals x minus 1. This is just equivalent to the log of 25 equals x minus 1. When I take the log of 25 on my calculator, I get 1.3979. And then I would just have to add 1 to each side, and I get 2.3979. All right, let's do another one here. Let's do example 11. Let's do log of 3x minus 2 equals 2. I think these are kind of fun. We want to see that there is a 10 here and then rewrite this. So we're saying 10 to the power of 2 equals 3x minus 2, or 100 equals 3x minus 2. 3x is 102, and then x ends up being 34. All right, let's go ahead and do another one. Let's do example 12. let's say ln of 2x plus 3 equals 4. Again, this is the same as log base e of 2x plus 3 equals 4. If I reformat here, I'm going to have e to the power of 4 equals 2x plus 3. Now, putting that into my calculator, e to the power of 4 is 54.5982. What I need to do is subtract 3 from each side. So I would have 51.5982 equals 2x. Then divide both sides by 2. And I get that x is 25.7991. Alrighty. I'm trying to figure out whether I should give you a word problem. I think I will. We'll make that our last example. Example number 13, just for good luck. All right, so example 13. Again, you don't have to write down all the words, just write down what I put on the board. So, how long does it take for $500 to grow to $700 at 3% annual interest compounded continuously, round to the nearest year? So remember, when we're trying to find the amount that when it's continuously compounded, we take the initial investment times e to the power of RT. So in this case, if we want to end up with $700, starting with a $500 investment at a 3% or 0.03 rate, we can set t equal to time and solve for t. The first thing that we would need to do is to divide both sides by 500. When we do, these cancel out and we get e to the 0.03t equals 1.4. Now again, we want to reformat. And by the way, I do have to say that reformatting is often a good idea when you're solving problems in this chapter. So we're gonna say log base e of 1.4 equals 0.03t. When I calculate the log, or ln, of 1.4 on my calculator, I get 0.3365. And then I would just divide both sides by 0.03 and I would get 11.2157. So the question was asking, how long will it take the money to grow to $700? It will take about 11 years, a little over 11 years. I hope this is helpful and I look forward to seeing you. Thanks, guys.